every odd number can be written as a difference of two squares. Proof: let x be an arbitrary odd number. By definition, x equals 2n plus 1 for some integer n. Now consider the consecutive perfect squares, n plus 1 squared and n squared. Then n plus 1 squared minus n squared is n squared plus 2n plus 1 minus n squared is just 2n plus 1. But this is just x. Thus, x can be written as a difference of two squares. Since x was an arbitrary odd number and we only use the fact that x was odd, we conclude that all odd numbers can be written as a difference of squares. Notice in this proof that the choice of n is a function of the arbitrary choice x. If we picked x equals 5, then we would know n equals 2. Or if we picked x equals 301, then n equals 150. The point is, we can construct n for any choice x. The sum of two rational numbers is always rational. Proof: let a and b be two rational numbers. By definition of being rational, there exists integers p1, p2, q1 and q2 such that a equals p1 over q1 and b equals p2 over q2. Then a plus b equals p1 over q1 plus p2 over q2, which simplifies to p1 q2 plus p2 q1 over q1 q2. Since p1 q2 plus p2 q1 and q1 q2 are still integers, a plus b is rational. Moreover, the choice of a and b were arbitrary. Thus, the sum of any two rational numbers is still rational. In the preceding proof, you need to avoid a noob mistake.
Math mantra! Don't make a dummy mistake with dummy variables!
Suppose you wrote, since a and b are rational, a equals p over q and b equals p over q for some integers p and q, this is completely wrong. This asserts that a equals b. True, there is no problem in changing dummy variables. For example, the sum of I from I equal 1 up to n is the same as the sum of j from j equal 1 up to n. However, if you had used the same dummy variables in the preceding theorem, you'd have completely changed the intent of the expression. Generally,
Math mantra! The purpose of notation is to precisely capture our mathematical reasoning. It is the mathematics that create the notation, not the other way around.
for our final example, recall that a function f is even if f of x is equal to f of minus x for every x. Likewise, a function f is odd if f of x is equal to minus f of minus x for every x. While every integer is either even or odd, some functions are neither even nor odd. But it turns out that every function has a neat decomposition. Any function can be written as the sum of an even function and an odd function. Proof. Consider an arbitrary function f. Using f, we can create functions g and h, where g of x equals f of x plus f of minus x over 2 and h of x equals f of x minus f of minus x over 2. Notice g is even, since g of minus x equals f of minus x plus f of minus x over 2, which is the same of f of minus x plus f of x over 2, or g of x. We can also see that h is odd, since h of minus x equals f of minus x minus f of minus x over 2, which is just f of minus x of x over 2. Simplifying, we have minus f of x minus f of minus x over 2. But this is just minus h of x. Summing g and h, or f of x plus f of minus x over 2 plus f of x minus f of minus x over 2, we get 2f of x over 2, which is just f of x. Hence, f can be written as the sum of an even function and an odd function. Since f was arbitrary, any function can be written as a sum of an even function and an odd function. Here you should be asking, where in the world did g and h come from? The truth is, we had to find these explicit functions. And, despite appearances, these functions didn't pop out of thin air. We needed to do lots of scratch work.
Math mantra. Most mathematics come from being locked in a room and wasting tons of paper.
And when you find a beautiful idea, you keep this single sheet and burn all the evidence of failure. This is what makes mathematics